But in the past classes, we studied curves and how to find the parametric equation for the curves, and we use that to find the length of the curve, right? And also, we use that to evaluate the integral around the curve. So then we're going to study surfaces and how to describe the surfaces. And then we use a so-called parametric equation for the surfaces to find a tangent plane to the surface and to evaluate the area of the surface. And then in the next class, maybe we will study evaluate the integral over the surface, not over the domain. Domain is a flat, a two-dimensional surface, and we are going to evaluate integral over the surface. Integral could be the function, such like the temperature of the Earth, right? Then you want to say, what is the average temperature on Earth? Then you have to evaluate the integral of the temperature function, right? So how can we describe the surface? I begin with the graph, okay? Graph of function f, okay, involve two variables, and that will be over the domain D, okay? So what is the definition of graph of a function? Okay, so first of all, the function is defined on the xy plane, right? The function is defined on the xy plane. That's a D. Then this function gives you the graph. And this is also, this is a domain D, okay? I copied here. Then the points, okay, consists of three components. And if Z is determined by the function, which usually is height, okay, then you get a surface. Okay, that surface is called the graph of a function. So here, X and Y, and Z is in the domain. So right now, this domain D is embedded into the three-dimensional space in the XY plane in the three-dimensional space. Okay, so that's a picture. So it's clear. So graphs are surfaces, right? Graphs are surfaces. So somehow we already know how to describe the graph, right? We use an equation, z equals f of x. I tried to describe the graph in a slightly different way. What I'm going to do is I'm going to find a map from here to here, okay? Instead of, put the D in the, right? How can I do that? I have a point X and a Y, right? And I get a point X, Y, Z. So this is a kind of parametrization, right? So X is sent to X, Y is sent to Y, but you also get another component, right? So the point in coordinates was coordinate X and Y, I send it to a point, right? A point in the three-dimensional space, but Z is determined by the function. Okay. Okay. So this is a kind of a map. Okay. So you can, if you use three functions, so this is so if I change the variable now, usually we use a UV, okay, but you can use a XY, okay. If you use a XY, I have to describe. That's the notation problem here. Okay, so what I'm trying to do. Yeah, I can use this one. The X and Y is denoted by, how do I describe this? I cannot use F here because F is of a G. Yeah, let's say I use let's say use G, H, and E. Okay, so in other words, I have a G and the function of X and Y, that's going to be just X. H, that's just a Y. And the E, X, Y, that's going to be determined by F of X. Okay, so you have a, yeah, you have a map, right? And so this map, this point is also denoted by R, okay? So that means if you want to describe this map as a vector function, right? So it's X and Y, it's going to be, you know, G of X, Y, H of X, Y, usually have a 3 components, right? E of X, Y. Now in this particular case, it's just X, Y, and F of X, Y, okay? Yeah, if I don't want to introduce GHE, then I just use the vector function. So the vector function will be, yeah, this is a R, right? So the value of, yeah, the image of the point XY is going to be XYZ, Z is F of X, roughly speaking. Okay, that's his value. So this is going to be X and Y. Okay, okay. So we get a very natural. This is very natural parametrization for the surface. Okay, R is called parametricization of the graph. Okay. Using yeah, so of the graph of the F. Okay. Okay. So given F, I can have very natural parametrization here. So this is graphs as a special surfaces. Okay. Graph as special surfaces. Now another example is if we describe the surface in the following way: X, Y, Z, but this time and the Y is going to be a function of X, Z. You know, that's possible, right? And the X, Z are in the domain D. These are domain in the X, Z plane, okay? So the surface looks like that, the graph looks like that. This time, the graph looks like that, okay? Now, X, Y, Z, okay? So domain is in here, it's D, okay? So this is every point here and have corresponding point there, okay? So this is a domain D. Now you have then you get a parametrization for that D, for that surface graph, okay? It's similar. So first of all, we only have X and Z plane, and this is a domain D, okay? So that is a domain D, and it's here, it's the same domain, okay? So I'm going to construct R. So R, X, Z is going to be the first component Z, the second component is determined by F and Z, okay? So this is a natural parameterization. It's a map, right? It sends a point in a 2-dimensional space to a point in 3-dimensional space. If here's X, Z, and here's going to be X, Y, Z, but Y is going to be Fx. Okay, it's very similar to our problem. Right, so they are using graphs is very most important, most popular surfaces, right? But there are some surfaces you cannot use a graph. And for example, a sphere. Right, the sphere with radius R, right? So sphere with radius r. Okay, so the equation is given. Okay, so the sphere is not a graph of function, but it consists of two graphs of function. Okay, you can view it as it's a graph of two functions. Okay, so sphere actually consists of two graphs. Okay, the one is the epicenter, you can view it like z equals r squared minus x squared minus y squared, right? And another one is negative. Okay, and the domain, okay, both x, y are in the same domain. So the domain is a unit disk. Okay, so it covers, so you get one you get the upper hemisphere, other one you get the lower hemisphere. There's a common area is in this equator. Okay, it's a circle. Okay, when on the boundary. Okay. So this is it, right? Now we can parameterize this surface in a certain way. Then you find the one parameterization, you can find R. Okay. If you want to use x, y to find x, y. Okay. So it's x, y, and r squared minus x squared y squared. So this is a one parameterization. It's only cover, yeah. So this is the image of this, right? So this R is from D to the sphere. That's called S2, okay? And the image is only going to be the upper hemisphere. The image of this is the upper hemisphere. Okay. If you want to find, you can find another one so that the image is lower upper hemisphere. Okay. Right. Yeah. To visualize this mapping is how to do that. You have a disk here in the XY plane. It's R, right? So take an arbitrary point, then you find the corresponding point here. Then you go up, you find this. Okay, so this is the XY, and here's XY 0. That will be XYZ, right? So that is a map. Okay, R. Okay, it sends this point to that point on the sphere. Okay. Now there's another way to parameterize the sphere. Do you remember sphere coordinates? The sphere coordinates actually provide a parameterization. Okay, this is R, right? Okay, this is an arbitrary point here. So first of all, you have a feed, then you project it to here. So you get theta, right? So you can have a map R, and from this is a theta and the feed. Okay. So for the whole sphere, I can still cannot go to get I can get a whole sphere, yeah. So I is determined by, okay, I is determined by x, depends on, x is going to be sine phi. If the radius is r sine phi, and cosine theta, y equals r sine phi sine theta, and z is being r cosine phi, right? And phi, if you want to get a whole sphere, phi is going to be between 0 and pi, and theta is between 0 and 2 pi, right? So you get something, a rectangle. Here's 2 pi, here's a pi. Now, this is not a kind of a one-to-one correspondence, okay? Let's look at all this red line. Where is the red line going? When those two lines, this line, okay, is all mapping to this point, right? It's collapsed to this point. Okay. And yeah, let me find another color. Okay. Yeah. So this line is sent to here. Now, how about the other? Let's try another color. Yeah. So when theta equals 0, this is theta equals 0. Theta equals 0 is a point here. So when theta equals 0, okay, and I think phi can be from 0 to pi, so this is again the theta equals 0. Okay, it's the same as theta equals 2 pi coming back. Okay. So that is an image. Okay, it's not on the boundary of the rectangle. The map is not one-to-one. Right. So those two vertical lines are mapped to this great circle from north pole to south pole. Okay. Everything else inside is fine. Okay. And so that's it. So this is our parameterization. Okay. For the most area of the surface. Okay, for the most area of the surface, where's my okay. Right, so that's this is a nice parameterization. Now you can also write R and theta phi is R sine phi cosine theta, and R sine phi sine theta, and R cosine phi. Okay. So the input variable can be any, can be xy, can be theta phi, can be uv. In general, okay, in general, in the if you have a surface, okay, our general notation here is I'm going to use uv instead of here's the domain D. Okay, and we have uv mapped here. Okay, and that point will be R uv. Now, usually it's denoted by 3 components, right? So this is a 3 component. Okay, you get, yeah, R uv. I usually have 3 components: x uv, y uv, z uv. Okay. Okay, so those are the 3 components. Now let's take a look at where this horizontal line go. Okay, this horizontal line is a red line. Okay, let's call it red line. Okay, this is, yeah, there are many red lines there. Okay, red line, horizontal red line. So that means V is fixed, U changes, right? So V fixed, U change. It could be horizontal line, could be something like that, right? Okay, on the surface. And then you can also look at this vertical line, okay, in the domain. And where's the image? Image could be like that. So you get the net. You see, you'll get net. Okay, you'll get net. Okay? A curved net. Here's just flat net. Under that image, you get curved net. Okay, so that's why how to describe the surface. This is very important subject, because if you want to apply mathematics to medical science, you know, or even mechanical engineering, and you have to describe the surface of some object, right? And how to describe it, right? You needed to learn this. This is a first step to advanced geometry, okay? Like imaging, right? This imaging process, you heard about imaging process in medical science, and that requires, okay? So if you it's not like, you know, you study engineering, you don't need to know so much mathematics. Interdisciplinary area, you can do better, okay? I remember, I think electronic engineering, the chair was several years ago. I'm not sure if he's still the chair. And he has a PhD in mathematics, surprise, so no PhD in electronic engineering. Like he switched to electronic engineering, he did very good. Also, the computer science department, the former chair for 12 years, he has a master degree in differential geometry like this, okay, for master degree. Then he switched to the computer science department and get the PhD from University of Colorado, yeah, in computer science. So then he used mathematics to do imaging process, and he can do very well if if you learn it. Okay. And mechanical engineering also, if you want to describe some machine or like a cylinder, how do you parameterize a surface cylinder, and if you know this language, then it's very you can do very well. Okay. So let's do another problem. Okay. This UV is general variable. Okay. UV is general variable. UV are general variable. It can be R theta, could be theta, could be XY. Okay. Let's look at the cylinder. Okay. Let's look at the cylinder. The circular cylinder. Okay. The circular cylinder is described by the following: x squared plus y squared is going to be just A or R. Okay, and Z is between A and B. So this is a portion of cylinder, right? Now, can we parameterize it? It cannot be, cylinder is not a graph of any function. Cylinder is not a graph of any function, right? And I'm trying to find the parameterization. So what I'm going to do is I just needed to choose X, right? X actually use the angle here, okay? So this is a theta, just so it's R cosine theta. Y equals R sine theta. Z is still equal to Z. Okay, so that's it. So the parameterization. So you got Z, you got theta, right? Now theta is between 0 and 2 pi. And Z is from A to B. So you got this is a domain D. Right? So this is a map R. I can describe R using theta and Z. Okay, so the first component R cosine theta, second component R sine theta, and Z. But so imagine, this procedure, the mapping is just fold this piece of rectangle to make a cylinder. Okay, so you glue together this side and that side. Okay, you glue them together, you make a cylinder. Okay, so those are the two red lines, and over here it is going to be this line. Okay, you just glue them together. Okay, if you draw the line going this direction, here's a line, right, going this direction. What happens here? This is going to be line a circle. Okay, so you can see that you make a cylinder. Okay. Now you can extend the rectangle. You can go further, no restriction on the theta. Then actually when you overlap the cylinder, so the image will be overlapped at some points. Even right now, if theta is between 0 and 2 pi, including 0 and 2 pi, and when theta equals 0 and when theta equals 2 pi, the image will be the same, just the vertical line. Okay? So it's not necessary to get a very large domain D to describe the whole surface. You just find the largest possible domain. Yeah, you don't need to create any overlapping. Okay, if it's overlapping happens, then there will be trouble to find the area. Maybe you double count the area. Okay, if you just yeah, this is what we can discuss later. Okay, so those are the typical parameterization. Now let's go back to basic in algebra. Yeah, we learned that. So given vectors, okay, A, and another vector B, okay? So those two vectors span a parametric parallelogram, okay? And that's called the span by A, vector A and B. Okay, it's easy to draw. Now that is yeah, that's a parallelogram, right? Spanned by two vectors. Now, how do we find the area of this parallelogram? How do we find the area of this parallelogram? Okay, can we use the two vectors to find this area? So actually, the area of this parallelogram is A plus B, the norm of that. Okay, A dot B gives you the angle. Okay, recall that A dot B is going to be cosine theta, the length of A times the length of B. But A cross B gives you A cross B actually. A cross B, when you, this is a vector, the above one dot is number, is going to be sine theta, the length of A and the length of B. And sine theta, this is a theta. Sine theta is just the height of this parallelogram. So that's why the height times the length gives you the area of the parallelogram. Okay. All right, so we needed that. Okay. So now I'm going to consider a nice domain here, D. Okay, I'm going to look at this now. Okay, and here's the surface in the XY plane, in the XYZ. So I have a map R. Okay, and here's the point. Here's UV, right? So those are the curves. Yeah, let's go back. Yeah, just first of all, let's look at the tangent vectors. Okay, so take arbitrary point here. This is a horizontal line. So I get this curve, right? And then I use look at the vertical line and I get this curve. Okay, so those are the two. Those are the images of those two lines perpendicular to each other in the UV plane. And now you have this, right? Is going to be R UV is a function of U, right? So you get a curve. When U changes, you get a curve. So how can I find the tangent vector to this curve, right? So RU UV is a tangent vector to the I call this one is called a U curve, right? Yeah, because U changes, you get a curve. So U curve to the curve, okay? You can say U curve, okay, to the U curve. And then if we fix if we fix U, then RUV is a function, actually is a function, a vector function, right? Vector function of V, okay? It's a vector function. Vector valued function more precisely. It depends on you only, right? Okay. So then you look at the partial derivative with respect to V. So this will be a tangent vector to the V curve. Okay. So let's go back to the picture. So this is you will get tangent vector. It's RV. Okay, this is RV, right? The point. RV and more details, you can RV, right? And this will be RU, UV. Okay. Now, these two vectors, Okay. You can do a couple of things. One is you can use two vectors to find the tangent plane. Do you agree, right? So you can use just two vectors to find the tangent plane. Okay. Yeah, you can find this two. You can use these two vectors to find the tangent plane. Now, how do we find the tangent plane? Right? How do you describe the tangent plane? Yeah, let's go back to the picture here. Let me draw the picture again. Okay, so you have this curve, right, and have a tangent RU UV, and another one is this curve, and you have a tangent vector. Okay, so to describe the tangent plane at this particular point, at the point of P, right, tangent plane is spanned by those two vectors. The tangent plane at the point P, which is the image of this, is spanned by these two vectors. Okay, now how can I describe an arbitrary point on the plane? This is arbitrary point on the tangent plane, right? Has three components. So we have to introduce, if we have to describe a tangent plane, I need a, let's describe tangent plane using the following. Okay. There are two different ways to describe. You can parameterize the tangent plane. You can also use another one. Use the dot plot. Okay, this is a vector on the tangent plane, right? Right, the vector on the tangent plane, and but the cross product, okay, is a normal vector. It's perpendicular. Is perpendicular to the tangent plane, right? So, so I can describe that tangent plane, every arbitrary point on the tangent plane in the following way. If this is x, y, z, so x minus, and that point I call it x naught, y naught, z naught, okay? So x naught, y minus y naught, z minus z naught. So this is a vector on the tangent plane. So the dot product was this normal vector. It should be 0, right? And that's uv. Okay, so this is going to be 0, perpendicular. And here, I have to say that this is a vector is RUV, okay? At a particular point. All right, so this is one way to describe a tangent plane. You know, you can view a tangent plane as a surface, okay? Then you can parameterize it in a slightly different way. Okay, you can. That's the first equation, right? The second equation is parametric equations for the tangent plane. Okay, so for the tangent planes, think about this is R U, right? This is a R B, right? And the arbitrary point in the tangent plane. Okay, so what I'm going to do is I use I'm not going to use V. I can use a ST. Okay. So so this is R and the UV, right? So So now it's in the space. Okay, it's in the X, Y, Z plane, this space. So you have a tangent plane here, right? So how can I describe it? I'm not going to use R, I have to use a different notation. That's the problem. Yeah, we use okay. See, we cannot use the same R, right? Let's use R tilde, okay? So this is I want to describe this R tilde, okay? So R tilde depends on st. Okay, it's going to be consist of this vector plus this vector. Okay, so this vector is R uv. Okay, plus linear combination of those two. Okay, plus t. Okay. So and here uv are fixed. Okay, uv are fixed. Depends on where you choose a point. Okay. So the any vector, right? See, any vector here will be, if this is A, this is a B. Any vector in here, this is a V. V is going to be a linear combination of these two vectors. Okay. So this is there are two different ways to describe the surface. One is use equation X, Y, Z. Another one is you can parameterize the tangent plane. Okay. Now, what I want to say here is, well, let's find the example first. Okay, let's find the example. Okay, we consider the graph z equals x squared plus y squared. You are very familiar with this graph. Okay, find the tangent plane at the point. This point could be 1, 2. When x is 1, y is 2, so it's 1, 4, x is 5, right? So this is a point in the xy plane. It's this is a graph, okay? And some point is here, 1, 2, and 5, and you want to find the tangent plane to that point, right? So there are two different ways to find. Okay. Forget what we learned before. We have a kind of formula, right? So I find the parameterization. Okay, I find the parameterization. This is x, this is y. Okay, I have a map. Okay, the standard parameterization, I use x, y. Is going to be x, y, x squared plus y squared. Okay, right? And so that point is P, right? So the point P is R when x equals 1, y equals 2. That's 1, 2, and 5. That's a P, right? Okay. So what is the vector? X. Okay, Ix is 1, 0, 2x. Now y, 0, 1, and 2y. Okay. And I want to look at the cross product. The cross product is I, jk, 1, 0, 2x, 0, 1, 2y, right? Then the first component is going to be negative 2x, I. Second component is negative 2y, j. The third component is k, okay? So that's the three components here. So this is actually yeah, it's going to be okay. So let's look at the picture. What does it look like? How does it look like? Okay. How does it look like? Okay. I think okay, I think this is a tangent vector, and that is a tangent vector. Yeah, it's harder to draw it. Yeah, it's harder to draw it. But the cross product will be, yeah, this is another, this is right? The cross product is this one. It's pointed to the inside, okay? It's pointed to the inside, okay? So this is Rx, that's Ry, and this will be Rx cross product Ry, okay? It's perpendicular, it's a normal vector, but it's pointed to the inside, okay? Right. So to find, so you have two tangent vectors. So it's going to be 1, 0. When x is 1, here's 2. When y is 2, here's a 4. So those are the two vectors. Okay. We also get right. We also get this. When x is 1, it's -2, -4, and the 1. Okay. So to find the equation for the tangent plane, I just needed to minus x minus 1, y minus 2, z minus 5, the dot product, it's 0. Okay, so this is a normal vector. Okay, so you will get -2x minus 1 minus 4, y minus 2, plus z minus 5 equals 0. So that's one way to describe. Another way to describe the equation is going to be, yeah. Now you can simplify a little bit, okay? You can simplify a little bit, 2x plus 2 minus 4 plus 8, z minus 5 equals 0. Okay, so what kind of numbers do I have here? Okay, 10 minus 5. So z equals 10 minus 5 is 5, right? So z equals 2x plus 4y minus 5. Okay, so that's, it's a graph. The graph of this function will be a plane, tangent plane. Another way you can describe is as follows. ST, right? So that would be R 1 and 2 plus S R S 1 and 2 R X, right? And the T R Y 1 over 2. So here's a 1, 2, 5 S. I forgot what is the value. 1, 0, 2 T 0, 1 and 4, right? That is, yeah. Right. So you combine them. You will get 1 plus S, okay, 2 plus T, and the 5 plus 2S plus 4T. Okay, so this is another way to parameterize the tangent plane. Okay, so it's good. And that's two different ways because we're talking about parametric equations for the surface. And tangent plane is a special surface. Why not find the parametrization for the tangent plane? Right? All right, so now what else we can do? Okay, so look at, we look at the x, let's look at the u and the v, okay? So we have a domain D here, and then you have surface, right? Okay, this is a surface, and in the x, y, z plane. All right, I have a horizontal lines, vertical lines. Now this tiny bit, okay, is going to be that's called, yeah, this, I call it du, okay? This width is the dv. So dA is du times dv. It's the area of this small rectangle, right? At that particular point. That's the point is u and the v. So at this point, right? So integral of dA double derivative is going to be the area of d. Remember that, right? All right. So you add all those area of these rectangles, small rectangles together, then you get a total area. Now, how about the image here, right? Remember, you have this curve, right? Right? So that is the image of that piece. Okay. I want to estimate that and add them together. Okay. I want to estimate that. Okay. Okay. All right. I will get this. This is a du. So I can look at the tangent vector. Okay, tangent vector. This is r, right? So ru. Right. This is tangent vector, and this is tangent rv. Okay. Now, interesting thing is the arc length of this piece. Okay, this piece, the arc length of this piece actually is what I should say, yeah. Yeah, I want to estimate this area, okay? But the tangent vector could be very long, the tangent vector could be very long, right? So the area is actually this area we estimate called ds, okay, ds. This surface area, okay, can be estimated as is actually du times rv dv, okay? So that will be the du dv, okay? So roughly speaking, it's just dA. Okay. Yeah, remember, the cross product, right? The cross bar, the length is going to be the area of the parallelogram. And the area of parallelogram, then then approximation for that small piece, tangent vector, is actually is ru du, okay, approximation, okay? So from here to here, and the image is from to here. So if you just look at tangent vector, it could be a very long vector, but times du is going to be, yeah, so this is a, yeah, so this piece, okay, this piece will be ru du, okay? So that will be the almost approximation of that vector, okay? That is not vector, it's curve. Okay. And then this will be rv dv, okay? Yeah, multiplied by this. And the length is going to be the ds. Remember? Yeah, so the cross, so then this cross product, these two vectors is going to be the parallelogram and gives the parallelogram. The normal of the cross product of those two vectors gives the area as a parallelogram. The area of this parallelogram is a approximation of that area, okay? Approximation to the area of that small piece. Okay, so recall that you have a curve, right? You have a curve. Here's a A and here's B, right? And this is a point T, right? And this is the tangent vector could be very long, R prime T, okay? But if you want to look at the T and the T plus dt, and that small piece is going to be from here to here, okay? So how to describe it? And that piece will be r prime t dt. Okay, so the ds, that is ds, right? Is going to be the length. Okay, I hope, yeah. Right, so you get this. Okay, so it's similar here. Okay, now the surface area, clearly the area of this surface, I call it the surface called M. There's a surface area. What is yeah, L? You use S, okay? Fine, use S, surface. So that is a surface S, okay? And that is going to be just double integral of the surface and the ds, okay? And what is ds? And that is the area surface. Yes, that's kind of integral on the surface, but you can translate it to the double integral. The double integral will be, okay, the surface is an image of this, right? This is the image of image of the r, right? Image of d and the r. So this is an image of d. Okay, so that's why you can change it to dA. Okay, dA is just du dv. Great. So the surface, the double integral of the surface, you cannot do that, but it can be translated. You cannot evaluate, but you can translate the double integral of the domain. So that is our formula. Okay. All right, and well, let's take a look at some examples. Yeah, just briefly show you how do we get this formula. Okay, and here's the example. I want to just look at the graph first. The graph. Okay, look at the graph. Okay, x and y are in the domain D in the xy plane. Okay, so this is a graph. This is domain D. Okay, in the xy plane, and the graph is in three-dimensional space. Okay, this is well, it's harder to, yeah, this is a D and here's a graph, right? Okay. Okay. So we have a standard map. In the standard map, this is D, right? The standard map is going to be X, Y, and FXY. Okay. All right, so let's find out what is X, right? So this is going to be 1, 0, fxy. Okay, and the derivative of this is going to be 0, 1, f, y, x, y. Okay. Right, right. So so let's try this, and then we find the cross product. Okay, that gives you the normal vector. Okay, that gives you the yeah, that gives you, this is this is vector r x, right? This vector r y. Can you that? Then you get the normal vector, the cross product. Okay, so the cross product. Okay. So we're trying to find the normal vector. So how about the JK? Okay, 1, 0, f x y. 0, 1, f y x y. All right, so let's see. So the first one will be negative fxy. The second one is also negative xy, okay? The third one is 1. Yeah, you can look at the second one. Why is this? Yeah, look at the first one, right? Look at this matrix, right? Look at this matrix. The determinant of this matrix will be negative fy, f sub x, right? So this is a normal vector. There's a length okay? It's going to be fx squared, right? Fy squared plus 1, okay? So our ds is this one. dA, okay? And dA is a area element is dx dy, okay? In the xy plane. So the area, the surface area, is first of all is the double integral of this, right, over the surface of the graph, right? And now you can change it to the integral of this. Into the double integral, okay? So that is a special case. Okay. Now we can, we can look at the graph of the parabolic. Look at the graph of a parabolic. Okay, look at the graph of parabolic. So we want to know what is the surface area of this. Okay, so z equals x squared plus y squared, and x squared plus y squared is less than or equal 1. Okay, that is going to be the graph. Okay, now how do you find? Can we find the area? You know, lots of surfaces like that. We call the surface revolution, right? Do you remember this? You know, surface revolution. We generate a surface by rotating curve around the axis, and we derive the formula for the surface area, so you can do the computation. I think, I don't know, in math was 65 or 66. Okay, so that's called surface area of a special surface. We already studied that before. Okay. Yeah, we can derive the formula, you know. Yeah. All right, so let's take a look at this. Okay. Let's take a look at this, and all we have to do is, this is a domain D, right? Domain D is going to be the disk. Okay. So I will have this, okay? The partial derivative, right? 2x, fy, xy, 2y. So the area of this is surface, right? It's going to be double integral of this disk and the square root of 2x squared plus 2y squared plus 1 and dx. This is just double integral. Right. Then maybe we are able to find the surface area of a sphere. Right. Maybe we can find the surface area of a sphere. Right, we learned that the surface area of a sphere, but we never proved that. All right, so how can I evaluate this double integral? Well, this is over the disk, so it's very natural. Use a polar coordinate. Polar coordinate. Okay, so x equals r cosine theta, y equals r sine theta. So this is going to be the double integral of the of this r is between 1 and 0, theta is between 0 and 2 pi. So it's going to be 4r squared plus 1. And all side is r, right, dA prime. Okay, now you can use r from 0, right? It's 0 from 2 pi. And this, you can change it to the iterative integral. And then it's 2 pi, right? So let's take 2 pi out. Right, then you find you have to use substitution. You let W to be 4r squared plus 1. Okay, so dW equals 8r, right? dr. right? So then it's 2 pi. When I equals 0, it's 1. When I equals 0, it's 1. When I equals 1, it's 5. Here's a w to the 1/2. RDI is 1/8 dw, right? All right, so find the antiderivative. Let's say pi over 4. Antiderivative of w to the 1/2 is going to be 2/3, right? That'd be 5 to the 3/2 minus. So you can simplify a little bit, but not too much, you know. That would be pi over 6. Right. So that is the answer. Okay, we stop. Yeah, you cannot simplify the first one. Okay. But you can evaluate, right? Now I'm very curious about the sphere. See, we learned, remember, right? Recall that for the sphere with radius r, right? The surface area. You know, in high school, we already learned that this is a sphere, so the area of the sphere is 4 pi r squared. How did you get that? Now we can prove it. The question is, how do you parameterize the sphere? Okay, you can view it as a graph. It's become more complicated. It's better to use a parameterization, spherical parameterization. Right, so our parameterization is going to be theta phi, right? Remember, here's a sine, I think sine phi, cosine theta, and the radius is r, so it's r. Sine phi, sine theta, and the cosine phi, okay? So theta is between 0 and 2 pi, phi is between 0 and pi, okay? So that almost covers the whole sphere except in the overlap along the one line from North Pole to South Pole. That one line, the areas can be ignored, no area there. Okay. So that is the whole sphere. Okay. Then our D, right? Our D is going to be this. Okay. So this map sends a rectangle over to the sphere. Okay. You have to stretch some area. So it's send a rectangle over to the sphere. So you collapse these two sides to a point. So step 1 looks like that. Okay. Yeah. Step 1, you know, it looks like that, right? Then step 2, you glue these two together to form like a football. And this sphere actually, okay, stretch it. Okay. Yeah. Then you get a sphere. Okay. Step 1, step 2. That's how do you get the sphere. Okay. This is this map. Okay. Yeah, I did not draw it perfectly. This is let me erase this picture. Okay. Yeah, let me rescape. Okay. When you collapse to 2 points, yeah, you still have this y. Okay, it's going to be like that. Okay, this 2 goes this way. You know, yes, if you have these lines, right, and this goes like that. Okay. Then you glue those 2 together. Okay. Then you glue these 2 together. Okay. All right. So let's calculate this computation. It's negative r sine phi cos sine theta and r sine phi cosine theta and 0. Here's r cosine phi cosine theta and r cosine phi sine theta negative sine phi. Okay. Now, how do I find? I don't want to copy this. How can I find that? What I do is I put ijk on the top. Okay. So the cross product, right? The first one, the component, is going to be the cross product of this. It'll be negative r sine square phi cosine theta. Yeah. Okay. Let's rewrite this. Yeah. So first of all, it's a cross product, negative r sine phi theta cosine theta. Okay. This is I minus j. So this will be oh, this is there's r here, right? So r here. So here's r squared. Yeah, this is a cross product. So r squared. Okay. And the last one is going to be negative r squared sine phi cosine phi sine square theta minus r squared sine phi cosine phi cosine square theta. Okay. Okay. So actually, you can combine them into this because cosine square sine square theta is going to be add them together. It's going to be 1. So I do get the following. I get the following vector. All right. So there's a common factor you can take it out, right? Which is sine phi, right? You can r squared can take it out. Negative r squared can take it out. Sine phi can be taken out. You get sine phi cosine theta, sine phi. Why always have a cosine theta? I should have sine theta. Okay, let me double check. This should be sine theta. Okay, this is sine theta. Okay, this is a sine theta. Right? And then cosine phi. Okay. Now it turns out to be, okay, it turns out to be this vector, okay. Let's say, so this is a going to be vector, right? And here's a sphere. Okay, this is some point here, right? And right, this is a, so it turns out to be this vector is going to be a vector point toward the origin of this, of the center of the sphere, okay? The reason is if I, yeah, this vector, negative of this vector is pointed to that direction. Okay. This is a normal vector. Okay. You see, look at this. Okay. Right. The point here is going to be, it's going to be r sine phi cosine theta, r sine phi sine theta, and then r cosine phi, right? And this is a point. And now it's multiplied by another number, right? So anyway, the length, okay? So ds, okay, dA, okay? It's going to be, this is a unit vector. Okay, this is a unit vector, so just r squared sine phi dA. Okay, so this is the element, okay, area element. So now you can find the area of the sphere. The area of the sphere is double integral of the on the sphere, and that changes the double integral of r squared sine phi dA. And this double integral is on the rectangle, so it's from 0 to pi, from 0 to 2 pi, r squared sine phi d theta empty field, right? And we're going to get the area. Haha. So the area is this independent of theta. So that's why it's 2 pi r squared sine phi d phi. Then the antiderivative of that will be negative cosine phi, and the evaluate the end point, I get 4. Okay. We get the area of the sphere. Okay. Let's go back to let's go back to the picture here. See, sphere, right? And let me go back, describe the sphere again, okay? So I want to tell you which way is a tangent, what is a tangent vector, right? Here's a point, right? Average point. Now r theta, when theta increase, this is a theta, right? When theta increase, fix the phi, you get a curve like that. So it's going to be tangent to that vector, okay, r theta. Okay, was this is r theta curve, right? When the phi fixed, this is r theta. But when theta fixed, r phi is going to be, because phi is going to be from top to the bottom, right? So that is a phi. So it's pointed to r phi. Okay, now theta. Yeah, let's see which one. Yeah. So r theta plus r phi. Just a second, okay? So r theta plus r phi, okay, is going to be r theta. You know, how do you? Yeah. So x actually is pointed to inside. So this will be perpendicular to the sphere, and actually point to inside. So this must be something rho times r, okay? Because r is going to be this direction, right? So it's opposite direction, because use the right hand to look at the cross product. Okay, I stop here, okay, and then